Okay, so we're just going over 9.6 over 15. We want to show these two vectors are independent, and because they're solutions to an ODE or system of ODEs, I believe we can use the Wronskian lemma. We can check independence / dependence by evaluating it at a certain value of t. T equals, t naught. I think that might make it a little easier. We can make this just equal to 0, for example. Maybe let's try doing that. So at t equals 0, for example, this becomes A, and this one becomes B. Okay, so yeah, I guess A and B. So if A and B are linearly independent, then x1 and x2 will be linearly independent. So do we know if A and B are linearly independent? I'm not sure if we do. I'm not sure if we're given that. I guess A and B could be like the same vector, potentially. They're not both 0. That's all we're given. Okay. And what are alpha and beta? They're just real numbers. Okay. Okay. So I guess we might have to do two cases then. I think. This one's maybe a little tricky because okay, so this is the way I would think about to do it. I would evaluate it at t equals 0, and then I get this case. Okay, so then I would say if A and B are linearly independent, then x1 and x2 are also linearly independent. And if they're not, then we could maybe suppose that A equals like some constant times B and plug that back into our original equations and then see that those are actually independent. That would be like my guess as to how to do this. Or you can try just, kind of have to mess around, I guess. You could, how do I get rid of this? So you could maybe just write A as like A1, A2, and B as wait, are these vectors in R2? No, it's just an n by n matrix. Okay, well, that's a little unfortunate. Maybe we could do the 2 by 2 case and try to generalize. What if A is 0, then they can't be linearly independent. Yeah, if A is 0, it does seem like that. Wait, did I evaluate these wrong? At t equals 0? At t equals 0, this becomes 1, this becomes 1, this becomes 0. Yeah, I think that's right. How do we know that x1? So we know x1 equals A and x2 equals B just because I'm evaluating it at t equals 0. Yeah. So, this one's interesting. We know that, okay, so we do know we are given, let's do, we are given that A plus IB is an eigenvector. Okay. Okay. So maybe we can kind of use that. And we know that A minus IB is also an eigenvector of A. And we know that these two vectors are linearly independent. Yeah. So it's interesting because it's kind of actually, it's easier to show independence when you don't have cosines and sines, when you just have e to a complex exponential. So it might be easier to take certain multiples of x1 and x2. I don't know. In any case, let's see if we can try to figure this out. I mean, if these two vectors are linearly independent, let's call these vectors something. I think we should be able to say that, you know, v1 plus v2 and v2, for example, are linearly independent. And then we should be able to say that so v1, right? The reason I'm doing that is because v1 plus v2 equals a. Right? Because if we can show a and b are linearly independent, that would show x1 and x2 are linearly independent. And then we want somehow v1 and minus v2 to also be linearly independent. So these are linearly independent. Which actually, yeah, this should imply that A and IB are linearly independent. Or just B, in fact. Something seems wrong here. I'm not sure if this is correct. Yeah, because someone said, like, what if A is 0? That seems weird. I mean, it could be, right? Yeah, I don't know how to do this one offhand. Personally, I think, okay, what I would do, I mean, it's something similar. Like, I would just rewrite x1 and x2 as complex exponentials. I would say, right, like I'd go through the book in 9.6 and I'd write, instead of 4 and 5, I would look at 2 and 3, the equations 2 and 3, W1 and W2. And I'd show that those are independent. Because so W1 equals e to the alpha plus I beta t times a plus IB. And this is the complex conjugate thing. Right, and then I would show that these are independent because x1 and x2 are just linear combinations of W1 and W2. So that's what I would do. I would show that. But I mean, this one's a little weird, I guess. I don't know. Um, let's see. You could try like, I don't know, maybe something else you could try is writing A as A1 through AN and B as B1 through BN. And then multiplying these vectors, so you get you're looking at e to the alpha t cosine beta t is A1 plus e or minus. Here's x1. And then you write x2 out. And you could try taking some linear combination and setting equal to 0 and just like making some argument there. So this is A1 e to the alpha t. And then if you take some linear combination, like C1 plus C2, you can try to argue that like if that equals 0, then the coefficients have to be 0. There's just like a lot going on. There's like a lot of different terms, so it gets a little confusing. I don't know. Do you mind if we move on from this question though? Maybe we can talk about it later, but we should probably try to get to Fourier series. But yeah, those are, anyways, those are three methods I would think to do this problem. I would either do this one, or I would do this one. You'd write them out as their complex exponentials. So see equations 3 and 4, or not 3 and 4, 2 and 3 in book. Or I would do, I would make some argument about their linear independence based on them being eigenvectors. Or I would try something like this, and then using linear independence of eigenvectors. So maybe we can flesh that out later. Okay, so why don't we transition a little? To Fourier series. So we don't have much time to talk about this, and there's a lot to unpack, you know. So we can start with this and see where we get. Okay, so Fourier series is essentially a generalization of orthogonal projection, or I guess not even generalization. It's a specific orthogonal projection. Is all it is. It's a specific orthogonal projection in a certain vector space. In a vector space of functions. Right, so let's just recall the definition of orthogonal projection. Let's say we have a subspace W and a vector V. So W is a subspace of some vector space. In this case, Rn. V is a vector. What is the definition of orthogonal projection? So there's just a formula for it, right? So in order to actually compute it, we need an orthogonal basis of W. So we need to pick W1 through Wn, let's say. No, not N necessarily, Wd. This is an orthogonal basis of Rn, not Rn, of W. And then the formula for the projection is V dot W1, and then you have to divide it by the norm of W1 because it may not be orthonormal. W1. So this is like projecting onto the line spanned by W1, and then you add it to its projection onto the line spanned by W2. And you do that for every component in your basis. So this is a review. Recall. Okay. And so now what we're going to do is the vector V is going to be replaced by a function, F. The vector space, actually, the vector space Rn is going to be replaced by a space of functions. These are going to be functions. Well, I'll define it in a sec. And W, this is going to be a subspace, is going to be actually all of V, but the orthogonal basis, W1, WD, this finite orthogonal basis is going to be replaced by an infinite orthogonal basis consisting of the functions sine nx and cosine nx for all n. Okay, and then we're just going to do the exact same formula. And this thing on the right-hand side, which is going to be now an infinite sum, because we're going to have an infinite basis, this thing on the right-hand side is going to be called the Fourier series of f. So we will call, I'll do this in quotes, proj f onto v, or I guess w, the Fourier series of f. All right, so let's elaborate a little, because we're going to need to define some things. So one, we want to define what our vector space is. So our vector space is going to be some v. And in that vector space of functions, we need to define what it means to have this dot product, right? What is a dot product of functions? So we need to generalize all of our notions before to make sense on functions. Okay, so let's do that first. So, well, our vector space of let me just say our space of functions are going to be, we're going to restrict our attention to functions that are defined just on an interval. We'll do it more generally from R to R, but for now we're just going to fix our domain to be an interval. Usually we let those interval endpoints be whatever, but we'll just specify it even more, from minus pi to pi. But the pi is not special. Oops. We could do like -1 to 1 or -L to L. You kind of just want a symmetric interval, so -L to L. So just functions on here, and with differential equations, we typically want those functions to be smooth, and that means that you need to be continuous and differentiable and twice differentiable and infinitely many times differentiable. But now we're going to relax those conditions, and there's some other conditions we're going to have. It's not quite so important for us right now, but we're going to want f to be some form of continuous. This is a continuous. It's not quite continuous. It's what's called piecewise continuous. And this is a same piecewise continuous. Basically just means you're basically continuous, except maybe at a few points you're not necessarily continuous. But you want it to be able, you don't, the whole reason we're doing this essentially is to consider somewhat nice functions. We don't want like really pathological functions. We want to make it a little easier for us. Okay, but the problem still remains, how do we define a dot product of these functions? And what does it mean to be orthogonal in that case, and so forth. So let's do that. So the dot product for Rn, right, this is going to be generalized to what's called an inner product. Right, so this is an arbitrary vector space. For us, it's going to be a vector space of functions. And anytime, and then we can just impose some additional structure on this vector space called an inner product. So what is this inner product? Right, an inner product needs to satisfy some things. So just like a dot product takes in two vectors and outputs a real number, an inner product is a function which we denote by these brackets. It's kind of a weird notation, but this means like a function which takes in two vectors, one for each input, the first and the second. It's a function from two copies of V. So this means it takes in two vectors of V. This is a Cartesian product. And it outputs a scalar. So the normal dot product takes in two vectors and outputs a scalar, and so does an inner product. And it satisfies some conditions, and it satisfies essentially the same conditions that a dot product needs to satisfy, which is you need the dot product of U and V, or the inner product of U and V to be the same as if you reverse them. You want it to be symmetric. You want, and then essentially you want this to be linear, just like a dot product is. I mean, this is linear algebra after all. So all these structures we defined throughout the class, throughout the semester, are all kind of linear structures. For example, when we had linear transformations, it needed to distribute over linear combinations. Vector spaces need to be closed under addition and scalar multiplication. Right? And this is the same thing, right? When we have Cu and V, we should be able to pull out this C. And likewise, I'll do another one. If you have U plus V, this should need to distribute. Right, this is linearity. Technically bilinearity is what it's called. This is called symmetric. And then the fourth one, which is what a dot product needs to satisfy in order to really give us a notion of length and angle, which is that the inner product of some vector with itself needs to be at least 0. And actually, if it's 0, then the vector itself is 0. This is sometimes called a positive semi-definite. Or definite, I actually forget. Which you don't need to know these names, but this is what a dot product needs to satisfy. And it'll be nice to know these conditions. We might test you on this, but the inner product we're essentially going to use on our vector space. So V I think in the class it was v sub pi, remember, was functions from negative pi to pi, satisfying some continuity stuff. Define the inner product on v pi by, and this is the one that we're going to use for Fourier series. So we need to define what it means to take an inner product or a dot product of two functions. And this is how we're going to define it. Okay, so this is our definition of dot product, right? This inner product is allowing us to talk about what it means to be orthogonal, what the length of functions are, what the angle between two functions is. They say all the things dot product gave us, this inner product is going to give us. And so we should just quickly check that it actually satisfies all four of these conditions. So number one is not too hard. If I switch f and g in this definition, do I get the same thing? Well, yeah, that's just switching f and g in this integral, but the multiplication of f and g is the same as the multiplication of g and f. So you just get the same thing. If I multiply this by a scalar, c, can I just pull that out of the inner product? Well, if I do that, I just end up with a cf in this integral. And yeah, I can just pull that c out of the integral. So that's true. If I have two functions, f plus h comma g, inner product, can I distribute? And so when I put that in, I just get f plus h in this integral. And yeah, that distributes just because multiplication distributes and integrals distribute, right? The integral of two things is the sum of two things is the sum of their integrals. So the first three are usually pretty easy to check. And then you just want to check the fourth thing, which is if you take the inner product of f with itself, is that always at least 0? So if I take the inner product of f with itself, I get the integral of f squared. And that's always going to be at least 0 because f squared is always a non-negative number. And so when you integrate a non-negative, or a function that always outputs a non-negative number, right? You're taking an integral underneath that function, you're always going to get a positive number or a non-negative number. So yeah, so it satisfies all four conditions. So this is our inner product. And this is what we're going to use to define Fourier series. So going back to this projection formula, we're just going to rewrite this with our inner product and our functions, and that's going to be the Fourier series. So projection of f onto w. Oh, right. So hold on. So the claim, which I'm not going to show, I think it was shown in the lecture, which is that the functions cosine, all these cosines, and then all the sines, these are all orthogonal. Is an orthogonal set in V pi. And we say with respect to the inner product, because we really need to define an inner product with respect to, this is with respect to inner product given before. So that's the claim. And then because this is an orthogonal set, we can project onto this subspace. And that's the Fourier series. So we'll do f dot cosine of x over cosine of x cosine of x. Cosine of x plus f dot cosine 2x cosine 2x, cosine 2x. So this is the Fourier series of f. It's going to be Fourier series. Right, all these things plus sines. Right, so it's easier to wrap this up into an infinite sum. So it's going to be, you're going to get a big sum over cosines. So I'm going to sum over the integers. Actually, typically you sum over the natural numbers for the, right, so I will say n is 0 to infinity. Okay, let's finish this out. Cosine nx plus the integral of f with sine nx. Okay, and so this formula is a little nasty, right? You have to compute all these things, but fortunately, you can just compute all these beforehand, and then you just plug it into the formula, right? Because, so this is the Fourier series, but you know, these and these can be computed beforehand. And so then you can just replace, you know, all of these with their formulas. And so that's usually how it's written. So I'll write it again differently. So the statement is that these inner products with cosines in itself, these norms, have a specific formula, right? So in fact, actually all equal pi, except for n equals 0, except for cosine 0x. So that's kind of a separate case, but they all equal pi. Otherwise, it equals 2 pi. And so the point is now we can simplify this and define the Fourier series probably as it's defined in the book. So I'll write it again here. So it's a sum of an cosine nx plus a sum of bn sine of nx. So here n is going from 0 to infinity. Here n is going from, I'm going to go from 1 to infinity because the 0th case is a little different. As I said, for 0, you get a different norm. And I'll figure out this coefficient later. But where an is the inner product of cosine of f with cosine over pi, so that equals 1 over pi and bn is essentially the same thing but with sine. Okay, and a0 you have to divide by 2 pi over here. So in order to kind of keep the formulas the same for all n, so for it is to be true for all n, we write a0 over 2 because we need to divide by an extra 2. A0. Okay, and these are the formulas. So this is called the Fourier series of f. These coefficients here, this an and bn, are called Fourier coefficients. And this is just like kind of basically an approximation of f. Right? So the Fourier series is an approximation, just like a Taylor series is an approximation of a polynomial or a function of f by sines and cosines. Okay. Okay, so I mean, that's the formula, which is all well and nice, but maybe we should do an actual example. So that'll be nice. So let's compute the Fourier series of f of x equals x. All right, so just the linear function x, let's compute the Fourier series of it. Okay, so the Fourier series of x is the function f equals, let's just write it out, a0 plus 2 over the sum of an cosine nx plus the sum of bn cosine sine yeah. Okay, and so now we just compute all these coefficients. An is the integral 1 over pi, negative pi to pi, of x cosine nx. Okay, so why don't you actually try to do that? You know, I should try to compute that integral out. You might have to remember some calculus, some 1b maybe. I think this one you probably want to do integration by parts, maybe. So it's been a while, right? So let's see. Yeah, if you integrate by parts, you integrate cosine, differentiate x. So I'll do that 1 over pi. Okay, and then let's see. What does this become? Sine of n pi is 0 for every n. So actually, you'll notice we're dividing by n here. So really, we should do, this should be n greater than 0. And then we should do n equals 0 case separately. It's always kind of nice to do the n equals 0 case separately. So you don't like accidentally divide by 0. A0 is 1 over pi integral of x, which is 0. Okay, so back to here. This is 0. And then the integral of sine of nx. Right, you can integrate this, you get a cosine in this, but what's an easier way to integrate this? Right, an easier way is just to notice that sine here is an odd function. And whenever you integrate an odd function from negative L to L, you're going to get 0. Because sine is an odd function. So in fact, it's interesting. All of our ANs are 0. right? Is that surprising? Right, this is not surprising actually, because is x an even or an odd function, both or neither? Well, x is actually an odd function. And if you're writing x as a linear combination of cosines and sines, well, cosine's even and sine is odd. And so if you're writing an odd function, it should only be written as a sum of odd functions. So this is even, this is odd. And so you should only get bn's. All your an's should be 0. In fact, that's what we find. An is all 0. And so in fact, you didn't even need to do this work. You could have just said, because x is odd, all the coefficients an will be 0. Because cosine's an even function. Right? And then just go straight to the bn's. So now we can compute bn. We don't need to do 0 separately because b0 has the same formula. We don't need to divide or anything. Well, actually, maybe we should, since we're dividing by, well, b0 is pretty easy to do, actually. Maybe it's best to do both a0 and b0 separately, because you're going to end up dividing by n, and you don't want to accidentally divide by 0, as I said before. So you can just quickly see b0 is 0, just because if I plug in 0 over n, this whole thing becomes 0. Okay, so then we can finish integrating. We get x cosine nx over n, probably the negative sign. It's very easy to make mistakes in this integration by parts. We get cosine nx over n with the negative sign. Yeah, okay. Okay, cosine of n pi. So this is actually going to depend on what n is. So let's keep this like, I'll write it cosine n pi minus cosine negative n pi. And we'll simplify this in a second. Okay, and what do we get here? We get sine nx over n squared negative pi to pi. All right, let's simplify this a little more. Okay, let's do some simplification. What is this? Well, this is actually 0, right? Because again, for the same reason, sine is 0. Right, sine of nx is, if you plug in pi, you're going to get 0 no matter what you get. Okay. And then here, let's look at these terms. What is cosine of n pi? So sine of n pi is 0 always for every multiple of pi. Cosine of n pi, well, cosine looks like this. Right, and pi is here, and then 2 pi is here. So 0 pi is here. So multiples of pi, this end up oscillating, cosine of multiples of pi end up oscillating between -1 and 1. So depending on the parity of n, this is either -1 or 1. And this is either -1 or 1. But it's actually the same one. So this is, let's actually make it a little more specific. This is 1 and negative. So 1 is at 1. It's 1 if n is even. Because then you get 0 and 2 pi, you get all 1s. And if n is odd, you get a -1. And this one on the right is the same thing. And so it might be nice to do two separate cases. So we're going to get negative x over n times, so if n is even, then this is 1 and this is 1, and so they cancel, you get 0. So actually, if n is even, this becomes 0. And if n is odd, this becomes negative 1 minus negative 1. Wait, did I do that right? Oh, wait, yeah, wait, no. Something went wrong here. Did I make a mistake? You shouldn't just get 0, right? Does anyone see the mistake I made? Oh, this should be a pi here. Oh yeah, oops. I forgot to evaluate x at pi as well. Yeah, right, good catch, good catch. Okay, yeah, this is a negative pi cosine n pi over n, and then this is evaluating x at pi. Okay. Very easy to make mistakes. Okay, negative pi and then minus a pi. Yeah, okay. So this is, right, so everything else still stands. So if n is even, you get negative pi minus pi, you get negative 2 pi over n. And if n is odd, this becomes a negative 1. And so you get a pi, and this becomes plus pi, so 2 pi over n. Okay, so yeah, unless I made another mistake. Yeah, I think that's right. Okay, so the point is, our final answer, we can just put them back in. Isn't the sign before the second term a plus rather than a minus? Okay, let's just actually do this a little cleaner. Okay, so this is when you evaluate it at pi, and then let's evaluate this at negative pi. You get a negative pi. So you should get a pi. Right? Negative x evaluated at negative pi. Yeah, like I said, it's easy to make arithmetic errors in this case. Okay. So fact, it's probably easier just to pull everything out in the front. But anyways, our final answer, which I'm running out of room to say, is I'm going to erase this top part so I can write it on the same page. Right, so all these cosine terms are 0, and you get, right, so for n even, so like let's just write it out. It's without the sum first. Sine of x, what's the coefficient of that? It should be 2. Right, so the pi's cancel. You should get negative 2 over n for n even, and 2 over n for n odd. So sine of 2x will be negative 1. Sine of 3x will be 2/3. Right, just using this formula right here. Sine of 5x will be negative 2/5, and so forth. So a nice way to write this, I'm kind of running out of room. I'll write in the top left corner here, is you'll see this written a lot in this way. So it's 2 over n times negative 1 to the n. So a way to write things that oscillate is as negative 1 to something. So right, this term here is negative 1 to the, so if I write it to the n, then if n is even, this will be 1, and if n is odd, this will be negative 1. So a nice way to write this is negative 1 to the n. And then you have another negative sign, so that changes it. But so you'll often see it written like negative 1 to something, and that makes you able to write it just as a succinct, a concise sum. And this is the Fourier series of f of x. So I mean, most of the work is just computing these integrals, to be honest, because the formula you just can kind of memorize almost. It's the exact same formula as projection formula. You just need to then plug your function in and compute everything. And a good way to not make mistakes is to use oddness and evenness of your functions, because if you use the fact that x is odd, you don't even need to compute any of these. And if you don't need to compute them, that means there's fewer chances for you to make a mistake. And another thing to try not to make mistakes is just to take everything very slowly. So just with all your negative signs. But anyway, so that'll kind of most of the Fourier series. On Friday, we'll do maybe another example, and we'll talk a little bit more about Fourier series, and then that'll be it. So like always, I'll stay on for a little extra for more questions.